Hey, here's part 2 of the Investigation 5 review. So now we're looking at what is the charge. So an oxygen atom with 10 electrons is going to have a charge of -2. A beryllium atom with 2 electrons is going to have a charge of +2. A neon atom with 10 electrons is going to be neutral, right? Because we're looking at the number of electrons compared to the number of protons. All right, so what happens to an atom's charge when you add a neutron? Nothing. Only the atomic mass is changed. Because neutrons have weight, but they do not have, their charges are balanced. Okay, so what happens to what happens to an atom's mass when you add a neutron? The atomic mass is increased by 1 atomic mass unit, which is about the size of a neutron. Okay, so where does the probability model of the atom say that the electrons probably are? The electrons are probably near the nucleus. Remember, when we look at those energy levels, they start off close, and once that one's full, they'll fill up the next one, and then the next one. But yeah. Okay, so let's see. What is it called when a material tends to gain or lose electrons when it is rubbed? Triboelectric. It means it is triboelectric. Okay, so show what happens to the charges on the ground when a negatively charged thundercloud comes over. So this is that idea of why neutral charges, why something charged is attracted to something neutral. This is what happens. So first thing I'm going to do whenever I have to show a model of like where the charges are going or how they're interacting is I'm going to set up my positive grid, because you guys remember that protons and neutrons pretty much don't move. They stay in the nucleus, and the electrons are the things that shift. So there's a lot of ways you can think about how this works. You can think about it like in the ocean, the positive charges like the coral reefs that stay put, and then the electrons are like the fishes that swim all around them, as one example. So I'm going to go ahead and make my positive grid here. And I'm going to show that this negatively charged thundercloud is like this. And the reason why it's negatively charged is because those charges separated, because thunderclouds are also triboelectric. So whenever you're making a model like this, it's good to make sure that you kind of show like where all the charges have gone to, because it's not like you can ever have charges all by themselves. Like you can't just have a negative charge that's not caused by something else. These charges have separated because of the clouds rubbing together, okay? So then if this was neutral, what it would look like is just a pair of charges down here, right? Each one of these would have an electron right by it to show that it's balanced. But what ends up happening is that this negatively charged cloud repels the electrons in the ground. So I'm going to show that these electrons are pushed down, and what that does is it causes this charge differential, meaning that this electricity that's built up here is attracted to this positivity that's down here, that's caused by the negativity here, and that is going to cause a lightning bolt sometimes. Or if there's a building with a lightning rod there, basically the electrons in the sky are going to take the path of least resistance to balance out the charges. So it might find a pathway through the air, or if there's a lightning rod on this building over here, it might be conducted through the lightning rod and down into the ground. these negative charges are trying to find a way to balance themselves out. Okay, let's see. So show the path of the electrons. I'm going to grab my squiggle tool here, and I'm going to draw it, and then I'm going to make it more visible. So the electrons come, they come from the clouds up here. They go through the lightning rod because that's a good conductor. Basically, they're following the path of the conductor. So they go through this first bell. That ball is attracted and grabs them and brings them over to this bell. And then they go through the wire and down into the ground. Because basically the big idea here is that these negative electrons want to balance out the positive electrons down here. So they're going to follow the path of least resistance to get to the most positive charge, which is in the ground. Okay, so let me make that more visible. Let's make it like a nice green. How about a nice orange? Orange is just great. Okay, now you can see it really well. Yeah, through the lightning rod, the bells, wire, and into the ground. Okay, so we're going to show the path of the electrons here by drawing arrows. I'm going to use my squiggle tool again. So the big idea here with the Van de Graaff is that the electrons are drained out of the metal sphere into the rubber band here and out into the electrical grid. There are some electrons that are coming in to power that rubber band spinning, but the positive electric field, excuse me, the positive electric field is caused by these electrons draining from the metal sphere and out into the electric grid. So I'm going to show that with orange again, make it bigger. Yeah, and since it's pulled out of the metal sphere, it's going to try to get those electrons from the metal plates, right? Like everything is kind of like a network. So if there's starting to be a pull of electrons somewhere, there's going to be another pull that's trying to replace those electrons. And if that pull keeps happening, that's how we get electricity, is that pull of electrons coming through a system. So how is the positive electric field around the metal sphere of the Van de Graaff created? The positive electric field is caused because electrons are drained from, and that's what that rubber band does. It spins, and the combs, remember there's a comb up here, and there's a comb down there, and they pull electrons from the metal sphere, and then they pull electrons from the, and I say they, we shouldn't use it or they. The comb on the top metal sphere pulls electrons from the metal sphere, which then pulls them from those plates into the rubber band, pulls it here into the electrical grid. Are drained from the metal sphere and the rubber band and pulled out into the electrical grid. So really it's the same kind of phenomenon that's happening with the lightning, right? That there's this pull of electrons one way to another. Or like not necessarily lightning even, but just like with the Franklin spells. So please explain what is likely to happen between this sodium atom and this chlorine atom. Why? And I have already kind of shown you what's going on here because the valence electrons are circled. Remember, the valence electrons are the ones that are on the outer energy level. And sodium has just one valence electron. Chlorine has 7, and they both can have a total of 8 valence electrons on that outer energy level. So that one valence electron from the sodium atom is going to jump over to the chlorine atom, which is going to give them both a charge, and that's going to cause them to like stick together like magnets, right? Okay. But really it's like the electric force that's causing it. Okay, the sodium atom will lose its one valence electron. And so it has only one, so it has a full outer energy level, and the chlorine atom will gain it to complete its outer energy level. So when sodium loses that one, then that outer energy level just basically goes away. Like there's nothing to fill it up, so it's just like not there anymore. So now this is the full outer energy level, and now this one has a full outer. Okay. So what charge will the sodium atom have after this happens? The sodium atom will have a +1 charge because it's lost an electron. And the chlorine atom will have a -1 because it gained an electron. Okay, last slide before the MSA extensions. I guess I'll just plug my computer in and keep going with the MSA extensions next. Before this kid got on the slide, he had an overall neutral charge. Now he has a positive charge. Assuming that the slide is made out of some kind of plastic, and noticing the kid has shorts on, show where the electrons went using the charges. Let me just pause right here, and I gotta plug my computer in. Okay, so what I wanted to show you is this diagram here is actually really important because that shows us what things are going to tend to lose electrons and which ones are going to tend to gain them. So assuming the slide is made out of some kind of plastic, it's going to be likely to gain electrons. And noticing the kid is wearing shorts, that means that there's likely going to be electrons coming off of his skin. So I'm going to start off, we can always start off with our grid of positive charges. And if this kid was neutral, each one of these positive charges would have an electron right by it, right? So I can show you what that would look like. Okay, so, but as this kid has gone down the slide has actually pulled off those electrons. So now the electrons are like kind of on the slide like this. And that's what happens there. And so this you can actually see the positive electric grid from his hair because all of his hairs are repelling each other because they all have a lack of electrons. Not no electrons, but they have a positive charge because those valence electrons that can be lost have been lost, okay? All right, so if the kid got off the slide and zapped someone, who gains the electrons from the zap? Does the kid gain the electrons or the other person? So this kid is the one that has the positive charge. He's the one that's missing the electrons because he gave them to the slide. So when he touches somebody, he's going to gain their electrons. I think both people are going to feel that shock, but he's really the one that's gaining the electrons. The kid is the one that lost the electrons. So when he zaps someone, it's because their electrons are going to him to balance his charges. Okay? All right, so that's this one. I'm going to stop this video and then I'll make another one for the MSA extensions.